Hello everyone, my name is Johannes, and myself and James and Ronan are going to present you a little random selection of the physics which is going on at the University of Strathclyde. And you see here we have pretty different topics that we talk about. First I'm going to talk about light sources, then we have James talking about very cold matter, then we have Ronan talking about very, very hot matter. Where's the pointer? Yeah. Very, very hot matter. And in the end, the other James is going to talk about matter, which doesn't actually exist on Earth, but you will find it only in space. So you see, these are very, very different topics, and in fact, it can happen that two random physicists meet somewhere and have a hard time understanding each other. But hopefully today you can appreciate that all these things are linked together in some way, and there's actually quite an overlap in between the different topics. So let's first talk about the light sources. Now, what is light? What we are considering here is that light will consist of particles. You may have heard already that this is not entirely true, or at least if we consider the light being particles, these particles behave in a very, very strange way. However, for what we are going to talk about today, this is a very useful assumption. But keep in mind that if we draw this little scheme with this little particle here flying around, this is just a visualization, which is very useful, but not quite true. And you know that light comes in quite a lot of different colors. It comes in red, in green, in blue, or violet, and the color of the light corresponds actually to the energy per particle. What comes out there is that a red particle, like the one here, has a rather low energy, and blue particles have a rather high energy compared to that, which is illustrated here by having it drawn bigger. Now, the light sources that we are working on at the University of Strathclyde are basically light-emitting diodes, which you may have seen already. They're electronic devices, and if you apply a voltage, they will shine in different colors. And you've seen them probably as indicators or something in your computer. So you might ask, what is new about LEDs? So the LEDs that we are working on are quite small. They're much smaller than a millimeter. Much smaller than a millimeter. Very, very small device, and still quite powerful. And they're emitting in the ultraviolet, which means that we have rather high energy light coming out there. Now, we don't want the world to be just in ultraviolet. We want the world to be in many, many colors, so we might want to convert the light which is coming out of these ultraviolet LEDs to any color that we want. So we want to take just some blob of carefully selected material, and this is illuminated by the LEDs, and out of that material then we have a photon coming out at a different color. So what would you think? What might be an appropriate material for this? Well, I'm going to tell you, it's actually certain types of plastic that we use for those. And we do not use these plastics only for the color conversion of the light, but we can actually use these plastics to build lasers out of these. So here you see the demonstration of a plastic laser. And of course, we're not building these lasers just because they give nice shiny light, but there are some applications for lasers. And typically, these applications involve the interaction of the laser light with matter. And we're now going to hear two presentations on the interaction of light, first with very cold matter, and then I talk about the interaction of light with very hot matter. So let's first hand over to James, who is going to talk about very cold matter.
Hello everyone, I am James McKelvie, and I am doing a PhD on opto-mechanical frequency conversion in supercold atoms. Now, what we're interested in with this is studying how light and really, really cold matter interact. So what we're going to start with here is a little bit of cold matter. And here's a friend, Mr. Atom. He's going to be our matter for this little demonstration. Now, as you can see, he's very cold. He's got his slippers on, and he's got his hot water bottle there. Now, we want to study how Mr. Atom interacts with light. So, we'll hit him with some laser energy. And as you can see, he doesn't really like that. Now, what happens when we have matter and light interacting? Well, what we can get is motion. Translational motion. You can either move forwards or backwards, up or down, even left or right throughout the laser beam, depending on certain criteria. Now, if Mr. Atom is part of a molecule, you can also get rotation, so that Mr. Atom and whatever friend is in the molecule will rotate to align themselves or out of align themselves with this laser beam. Now, that's not the only interactions you can have between matter and light. However, to see what else we get, we're going to have to take a little closer look. So we use a magnifying glass. There we go. Now you can see here there's a bit of a more detailed structure inside Mr. Atom than just this crude drawing that I've taken the liberty of making. Now we've got electrons. And electrons, when hit with this laser energy, gain energy. If this laser energy is sufficient, it can boost our little electron here that is in the ground state. So here's the ground floor. Think of it like a house. Here's the ground floor, and that's where the electron is. If there's enough energy in this laser beam, then it gets enough energy to jump upstairs. Now, that's just one atom and one electron inside that atom. But we're not looking at just one atom. It's really difficult to look at one atom. What we're going to look at is many atoms and many electrons, and how the electrons vary in their ground state to upper state with this laser energy. So here we have Mr. Atom and all of his friends being excited in various ways and being stimulated by this matter, by this energy, sorry. And next, to talk about hot atoms interacting with lasing material, is my friend Ronan Burgess.
Right, hi there, my name is Ronan Burgess, and I'm going to talk about a bit of the research that I do at Strathclyde. So, I also deal with shooting atoms with lasers, except my atoms are slightly different. We had Mr. Electron sitting in his upper floor of his house, but when I take him, I don't leave him there, sort of blast him straight out, which gives a completely new state of matter. We now have a matter where we have Mr. Atom and Mr. Electrons all floating about, and it's something you may have heard, it's a state of matter called plasma. So here we've got a ball of plasma here. This is the sort of thing you'd find out in outer space. The sun is made of plasma, and the other stars, or space itself, is just a really, really dilute plasma, which basically means we've got lots of atoms and lots of electrons sort of floating about together. Or sorry, atoms that have lost their electrons and therefore are known as ions. So I take my collection of electrons and ions and I blast them with a really intense laser pulse. And what do I mean by really intense? Well, if you've ever taken a magnifying glass and focused down the sun on a warm day, you know you can get quite a hot spot. Well, our lasers are the equivalent of, if you take a magnifying glass about the size of the Earth and focus down all the light coming in down to a single spot, if you can think about how hot that would be, that's about the sort of power of laser we're using. It's not quite that powerful, but it's pretty close. So what happens is we fire this laser pulse into our plasma, and the light, the force of the laser pulse, is actually able to push the electrons in the plasma out of its way. So the electrons go flying out of the way, and then they always go back to where they were, so they all come rushing back, but they tend to go too far, which means they repel against each other, because electrons don't like being close together, so they rush back out again, and they end up oscillating in the plasma behind the laser pulse. If they're moving, it means they have energy. So we can see here, we've got our laser pulse comes in, it sets up this wave behind it, and we see here this is the energy. Before the laser pulse, there's no energy in the plasma, and afterwards we've got energy stored in this oscillating field in the plasma. And this field is known as the wake field. Next thing we do is we take an electron bunch and we jam that into the plasma as well. As I said, electrons don't like to be together, they tend to repel each other. So now when our electron bunch comes in, it also forces the electrons in the plasma out of its way. And it's also going to set up a wake field behind it in the plasma. This time it's slightly different. It's not the laser that's pushing them out of the way, it's called the repulsion, Coulomb repulsion. But we end up with these two wake fields. And these two wake fields are going to interfere with each other. So, interference. If we take two waves, like the red and the green one here, these two waves are almost in phase, which means that the maximum occur near the same point and the minimum occur near the same point. If we add these two waves together, then these two maximum add together and the wave grows, the minimums add together and we get a deeper trough. And we see that the two waves are added together to give us a larger blue wave, and this is known as constructive interference. On the other hand, we also get destructive interference. We can see at the bottom here, the red and the green waves are almost out of phase. So we have the maximum combining with the minimum, and we end up with a very small blue wave here. No, this is destructive interference. So, in our case, we have our laser pulse with its wake field, and the electron bunch with its wake field. These are going to combine together, and we can see that here they interfere destructively. The wake field is being decreased from before to after. This means that since the wave is decreasing, the electrons in the plasma are moving with less energy. So we can see here that our energy in the plasma is decreased. This energy can't be destroyed. It's actually being transferred into our electron bunch, which means our electron bunch is gaining energy and accelerating. And what I work in, you can see the title here, laser wake field acceleration, is about getting as much energy into these electron bunches as possible. The more energy you get into the electron bunch, the more useful they are. If you can get very, very high energy electron bunches, they have a lot of applications. One of the things you can do is you then stick them through very strong magnetic fields and you make them wiggle about really, really fast. And they end up emitting really useful radiation. So lasers we've seen tend to operate in the color region or even UV. These can actually produce X-ray lasers, which have a huge range of sources. This is all done in a lab like this one here, which looks a bit jumbled, but is actually very, very expensive, and is a good reason to become a physicist. People will give you millions, literally millions of pounds to build labs like this because you've said to them, I want to shoot things with lasers and see what happens. You can also get more money for saying, I want to build a bigger laser. But sometimes it's hard to get all this money, so what I do is I actually do it on just a desktop computer. I program the computer to simulate what would happen when we shoot atoms with lasers and look at the outcomes, which means that we don't need to build big labs like this to do all of the experiments. I can come up with ideas and theories on what might happen just based on my illustrations with a computer. So this is computational physics, which is actually quite common, and I'm now going to hand you over to my colleague, a fellow computational physicist, James.
Hi, I'm James Miller, and as Ronan was just talking to you about, I do computational physics. Of course, there's computing, and then there's computing. The regular kind of computing, which I'm sure you're all familiar with, is just using a standard desktop of this form, the kind that you'll presumably all have at home. Scientists often use computers for exactly the same things as you will, doing our homework, writing our reports, surfing the internet, but occasionally we require them for a bit more intensive work, and the kind I use is HPC, high processor computing, which looks more like this, weird space-age blocks, and this is because they are equivalent to 1088 of the standard desktop processors stapled together, is what we use in the University of Strathclyde High Performance Computing Cluster. It's got 100 terabytes of storage, which is a lot, and a top speed of 13 teraflops per second. Now, if you get a standard human to do perhaps a multiplication question, they'll maybe get it in a second if they're good. 13 teraflops per second is equivalent to 13,000 billion calculations per second, so it's quite fast. So what do I use this to look at? Well, astrochemistry, essentially, all the chemistry that's too awesome to be done on Earth. Now, you might initially think that surely astrochemistry can't be a very big discipline, because space is empty, right? And indeed, it is true that most often we just have the individual extremely cold atom wandering around in the void, not doing very much. Of course, space is an extremely big place, and it's not all like this. There are quite a lot of much denser environments, still less dense than the kind we get on Earth, but impressive nonetheless. And what I look at in these environments specifically is water. Now, of course, because it's in space, it's very cold, and water turns to ice. On Earth, you get orderly, regular crystalline ice, which everyone's familiar with, gives the familiar shapes of snowflakes. And the reason it's orderly, and we get hexagonal structures like this, is because of the nanoscale ordering. On the scale of 1,000th of a millionth of a metre, we can see the individual atoms, and in normal Earth-based water ice, they're all packed into a nice orderly cluster, and it's all very sedate and civilised. When you put water in the fridge, everything cools down slowly, and you get a nice orderly lattice. In space, this sort of thing doesn't happen. In space, you get ice that's pretty messed up. Stuff like this, which is essentially no structure at all, completely amorphous, wacky ice that's all over the place, just forms long tubular structures, and you get it essentially by hurling individual atoms, a grain of dust, a micron across, at about 100 meters per second. And my specific job is to learn exactly how crazy this ice is, depending on how fast you throw it, and precisely how cold the underlying speck of dust is. So, to summarise all our talks together, basic physics, the kind that everyone's learning in schools, is the foundation of all the research we do at Strathclyde. It's all based on the normal things you'll read in the textbooks, from nebulas to plasmas to lasers to space ice and even the freezing Mr. Atom. Everything we do is just based on relatively simple principles that you can find already in textbooks. Research can be very exciting, as we've seen. You get to blast things with lasers and look at stuff in outer space, and so I'd encourage you to come and study physics at the University of Strathclyde. Thank you.